This lecture focuses on conjugate direction methods and quasi-Newton methods for unconstrained optimization. And let's start by defining the conjugate directions. Okay, so here we have the definition. Given a positive definite n times n matrix Q, the non-zero directions d0 through dk are called Q conjugate if the following holds. So we have di transposed times Q times dj is 0 whenever I is not equal to j. Okay, so it's almost like orthogonality, but in this case, you have orthogonality when you look at di and q times dj. All right, so essentially the vector di is orthogonal to the vector q times dj, and we can show that if we have k plus 1 q conjugate directions d0 through dk, then they will form a set of linearly independent vectors. Because they're linearly independent, we cannot have more than n Q conjugate directions, right? So because we can have at most n linearly independent vectors in n-dimensional Euclidean space. This is a proof that they form a set of linearly independent vectors, which we'll skip. Next, we'll discuss how these Q conjugate directions can be used to develop an optimization method. We will focus on the convex quadratic case. This is the simplest case where these methods are interesting. We will look at the convex quadratic problem in the form minimize f of x, where f of x is a convex quadratic function. So the Hessian is given by Q, and we assume that Q is a positive definite matrix, so we have convexity. What we do in the conjugate direction methods, we are actually using a set of Q conjugate directions as the directions along which we move in each step. Okay, so let's say if I had n Q conjugate directions, the way I would proceed, I would first start moving along the first of these directions, say d0, right? So say I'm at the point x0 to start with, and then we take the direction d0 and we move along the direction d0. I would get the point x0 plus some step size alpha times d0. All right, so and then the direction d1, the next direction that we would use is Q conjugate to d0. So this is my x1, right? So and then say if direction d1 would go this way, then my x2 would be x1 plus alpha 1 times d1, and so on. We would proceed this way along this Q conjugate direction. So then the next one would be d2, which is Q conjugate to d0 and d1. So I mean d0, d1, and d2 would form a set of Q conjugate vectors in this case, and then d2 would be the next direction that we are using, and we would proceed this way. Okay, so now how do we select the step size alpha k? We could do it similarly to how we have done it in the steepest descent method. So essentially we can try to select the best possible step size, which would mean that I'm minimizing the function f along this direction. Okay, so let's say for x0, I start at this point and then I'm moving along the direction d0, and I'm trying to find the very best step size that will give me the smallest possible function value as I move along this direction. So and this corresponds to minimizing this function here, f of xk plus alpha dk in general. So for the first step it would be f of x0 plus alpha d0, right? And I'm minimizing it with respect to alpha. So, and unlike with the steepest descent method, here we allow to actually have an arbitrary alpha, a real alpha, okay? So it doesn't have to be positive, it can be negative as well, okay? So if the direction d0, let's say, points this way, potentially we could move actually in this direction also. Because we are dealing with a quadratic function, we can actually compute the optimal alpha k, the step size, analytically, similarly to how this was done in the steepest descent method. Here we have the derivation for the optimal step size alpha k. All right, so what we do in this case, we again represent the function f of xk plus alpha dk, so which is for fixed xk and dk, it becomes a function of a single variable alpha. We denote it by phi k of alpha, and now what we need to do is to minimize this function with respect to alpha. So this is a one-dimensional problem, and we can actually spell out this function phi k of alpha explicitly, because we are talking about f of x, which is given by 1/2 x transpose times q times x plus c transposed x. Then, instead of x, we substitute this argument here, xk plus alpha dk, so we use it for x. And then, as a result, our phi k of alpha can be written in this form here. And we can see that this is a quadratic function with respect to alpha. Because q is positive definite, this coefficient here for alpha square is positive. We can find the minimizer for this function by just looking at the negative of this here divided by the coefficient for alpha square. Okay, so and as a result, our formula for alpha k is given here. You can see that it looks similar to what we had in the steepest descent method, except for in the steepest descent method we had a very particular choice for the vector dk. So in the steepest descent method, dk was equal to minus nabla k, which is the negative of the gradient of f at the point xk. And then if we plug in dk equal to minus nabla k in this expression, we'll get the following formula. So we'll have alpha k is nabla k transpose times nabla k divided by nabla k transpose times q times nabla k, which is exactly the expression for alpha k that we had in the steepest descent method for convex quadratic function. Okay, so but now for the conjugate direction method, we have this formula here for a step. So if we are at the point xk, the next direction that will move along is dk, then our step is given by xk minus this expression for alpha k that we just derived multiplied by dk. This is the step that we will take. We also need to discuss how we actually select these q conjugate directions dk. But before we do that, we will first discuss some of the properties of the conjugate direction methods that will be important later on.
Very important!
One such property is that if we perform k plus 1 steps of the conjugate direction method starting with the point x0, then as a result we'll obtain the point xk plus 1, and the gradient of f at this point xk plus 1 will be orthogonal to every direction that we took using the k plus 1 steps of the conjugate direction method. Okay, so we have nabla k plus 1 transpose times di is equal to 0. Now, what happens if we perform n steps of the conjugate direction method? In this case, we perform the steps for I equal to 0, where we use the direction d0, then 1, and so on, up to n minus 1. Okay, so this corresponds to n steps of the conjugate direction method. So, and as a result, the point that we'll build will be xn. Okay, so and now let's try to see what happens to the gradient nabla n at the point xn, right? So we'll have nabla n transposed times di will be equal to 0 for all i's between 0 and n minus 1. di's are q conjugate, right? So they're all linearly independent. And we have n such directions already for I between 0 and n minus 1. So, and these n directions, they actually form a basis in Rn already, right? So now what happens if we look at the gradient of f at the point xn? So this vector nabla n transposed, so it looks like it is orthogonal to every direction from this basis. If it was orthogonal to every direction from this basis, it would mean that we can add it to the basis, right? And we would have a basis with n plus 1 vectors, so which is impossible, right? So therefore, the only way this can be satisfied is when nabla n this gradient vector is in fact equal to 0. So which would mean that after n steps, we would obtain a point xn where the gradient of f is equal to 0, and this is exactly the point we are looking for. So therefore, we converge to the global minimizer in this case in at most n steps. So our method will find the stationary point in at most n steps. A stationary point for a convex problem obviously is the global minimizer, right? So we have the convergence to the global minimizer of a convex quadratic problem in at most n steps here. We'll skip the proof of this and move on to the next property of the conjugate direction methods. In this property, we assume that instead of moving one direction at a time, we are given k plus 1 q conjugate directions, d0, d1, and so on, dk. All right, so these are k plus 1 q conjugate directions, okay? So, and assume that we have these k plus 1 directions. We are not given the step sizes yet, but we need to select k plus 1 different step sizes that we would use to move along these directions. Our goal is to select these k plus 1 step sizes in a way that after making the k plus 1 steps, we will get the best possible point we can get along these k plus 1 directions when we consider them not one at a time, but in a system. Essentially, given k plus 1 directions, I ask you to select k plus 1 step sizes simultaneously so that the resulting point xk plus 1 will be the best possible with respect to f. So the value of f at the point xk plus 1 is the smallest possible. All right. So previously in methods like the steepest descent, we would look at one direction at a time, and we would select the best point along a single direction, right? So, and then we would select another direction and again select a step size. But what if we had an opportunity to select the best point along k plus 1 directions taken simultaneously? As an example, let's consider a two-dimensional case. Say here we have some level set for our function where our point x0 is located, so this is where we start. And then the global minimizer will be somewhere here, so this is our x star. Given two q conjugate directions, okay, so let d0 be a direction like this, and d1, say a direction like this here. So remember, we can move either way here, along the direction or in the opposite direction. So now we have these two directions, right? So how do we select the step size that will give us the best point after two steps? Okay, so how do we select these two step sizes simultaneously that will result in the best possible point after two iterations? We can see that actually we can always select the step sizes in the way that we'll reach the global minimizer after these two steps. Let's say this is d0, right? So then this is d1. So you'll draw this direction d1 on parallel to what we have drawn before, but so that it passes through the point x star now instead of passing through the point x0. All right, so and then we can clearly see that if we select our alpha 0 in a way that our first step will take us from x0 to this point here, which is the point of intersection of d0 and d1 that is drawn so that it passes through x star, then this will be our x1. And then we need to select alpha 1 when we move from x1 along the direction d1. So we need to select it in a way that we just go directly to the point x star. Okay. Obviously, if we select our alphas this way, then we'll end up at the point x star, which will be the global minimizer for our problem. You see here we are trying to select both step sizes simultaneously instead of, let's say, taking direction D0 first and then finding the best point along the direction D0, and then from that point we take the direction D1 and find the best step size along the direction D1. But instead we are solving this problem by varying alpha 0 and alpha 1 simultaneously. Let's consider a more general case where we have an n-dimensional problem, right? So, and assume that we are taking k plus 1 steps. The corresponding step sizes alpha 0 through alpha k are given by this k plus 1 dimensional vector that we denote by alpha k. What we need to do is to select the set of alphas here that will be the best for k plus 1 steps taken simultaneously, right? Essentially what we need to do is to minimize this function here with respect to the vector of a's. So here we use a's instead of alphas, and then the optimal values for a's will be alphas. Instead of alpha 0 through alpha k, we are using a0 through ak, right? So, and then if, let's say, we select a0 equal to alpha 0 here, so then this point would become x1, and then if we select a1 equal to alpha 1, then x1 plus alpha 1 times d1 will give us x2, right? So, and so on. After k plus 1 steps, this point, assuming that we select a's that are equal to the step sizes alphas, we would obtain the point xk plus 1. And now what we need to do, we need to select these a's in a way that will obtain the best possible point after k plus 1 step. So we want to minimize this function here with respect to the vector of ak's, right? So as soon as we fixed x0 and then d0 through dk, we are optimizing only with respect to ai's, right? So we write this down as the function of a k vector, right? And we need to minimize this phi k of ak with respect to the vector ak. Here we have this in the matrix representation. The result here is that if we are trying to solve this problem of minimizing phi k of ak, then the optimal set of step sizes will be given exactly by alphas that you have in the conjugate direction method when you are minimizing with respect to each direction one step at a time. Let's say for this two-dimensional case, what this would mean is that performing optimization with respect to two step sizes simultaneously is the same as if I took the direction d0 first and would find the minimum of f with respect to this direction, and this would be the point x1, and then at x1 I take the direction d1 and look for the minimum point with respect to this direction, then I would end up at the point x star. So doing minimization with respect to k plus 1 direction simultaneously is the same as taking one direction at a time and performing k plus 1 line searches to find the best point along a single direction at each step. This is a nice property to have, because instead of solving this k plus 1 dimensional problem, we solve k plus 1 one-dimensional problems. And one-dimensional problems are obviously easier to solve than higher dimensional problems. Again, we'll skip the proof here. So now, what this fact also means is that if I select n q conjugate directions and I perform the corresponding n steps, then the point that we'll get will be the minimizer with respect to these n linearly independent directions, right? So because q conjugate directions are linearly independent, and because n linearly independent directions form a basis in the space Rn, this means that after n steps we are essentially optimizing over the whole Rn, so we are finding the best point in Rn for our function, so we find the global minimizer in at most n steps. If we go back to this illustration of the steepest descent method, where we saw many steps of the steepest descent and it slowly converges to the global minimizer x star, we can use this illustration to compare the conjugate direction method with the steepest descent and with Newton's in the case of convex quadratic problems. So this is a convex quadratic problem here. Steepest descent is already illustrated here. Then with Newton's method we saw that we have the optimal solution for the convex quadratic case in just one step. So Newton's would just take you from any x0 directly to x star. Alright, so and what happens in the conjugate direction methods? Let's say if we select our first direction just like we did in the steepest descent to be the negative of the gradient, we can do that, right? So the conjugate direction method will take the same first step as the steepest descent, but then the second step will take you directly to the global minimizer. And of course this is a two-dimensional case, right? So for a problem with just two variables, this is what will happen. You will take one step like with the steepest descent, and then the second step will take you directly to the global minimizer. Alright, so in three-dimensional case it would be three steps, right? And so on.
Just keep swimming, just keep swimming.